Kissel from Allison Bob.
Hi, folks. Happy to be here. Once again, it's one of these wide rooms, and I feel so distant from Katie and company over there. And so I may pace back and forth. So I have this device. Just how shall I put this? This is a vendor presentation. The nature of vendor presentations is I'm going to be presenting work that much of which is not mine. Okay, now I also actually do present my own work from time to time, and so I'm a little uncomfortable doing this sometimes. But the important thing here isn't the discrete papers. There's about 6 papers from Allison Bob that I'm going to be touching on here. But it's really sort of the direction and the path and sort of, if you will, the particle track of this activity that I think is more interesting. And that's what I want to get across. And so the temptation may be on my part to drill in on some of these slides and some of this work. And I have to fight that because, well, you guys need a break at some point. So, briefly, I'm going to talk about Allison Bob and the cat qubit flavor that we do, and some of the implications of that, because this has positive, like anything else, this is engineering. Okay, it has some, we're getting trade-offs. I love the trade-offs that are made, and that's part of why I'm working with Allison Bob and part of why I think this is an interesting narrative. And then talk about the sequence of experiments over the past few years that Allison Bob's been able to do. And the things that we've been discovering just month after month, the little knock-ons that, make me feel good that this is a really legitimate path to pursue. So who are Allison Bob? It is a French company, relatively recent startup, headquarters in Paris. Most of the researchers are in Paris. There are a handful of us in the US, mostly working on partnerships with teams here in the US. About 150 employees, according to this slide. I think the number is actually a little higher than that at this point now. But the focus of the operation is to produce actually useful computational tools and not just devices that could be used for physics research. Although the physics research aspects are fabulous, the idea is to actually build something that I've been excited about building since 2006, when I first got exposed to quantum computing, is a quantum computing that does scientific computing for folks. So the key to all this is our cat qubits. There are a couple of flavors of cat qubits. These are dissipative cat qubits based on biased noise. What that boils down to is the superconducting qubit. So it's based on a supercomputing microwave frequency oscillator. The thing that's peculiar about it is that it is being managed. The photons are in the oscillator are being replaced constantly with biased pairs. And that allows us to preserve the state for a reasonably long period of time. And the way the device works, it is auto-correcting on one axis of error. And you can pick one. Most people tend to pick bit flip. We could use phase flip. It's a symmetric universe in that regard. So the more photons I have in the device, the more stable it is against bit flip. And that's an exponential effect. Okay, so we typically use, A for an arbitrary reason, or A or alpha as the photon count or the square root of the photon count. And the larger A gets, these are Wigner diagrams, which I was not familiar with until I started working with Allison Bob. I imagine they're reasonably familiar to folks here. So we're plotting out in the space. So if you look at it sort of here, the higher the value of A, sort of the further apart these two poles are, and sort of the steeper the gradient. And so the more it will tend to reinforce itself. This is fabulous. It's an exponential function. Of course, there's a price. The price is that my phase errors are going to increase. But my phase errors are going to increase by a linear factor. And frankly, when the founders of Allison Bob explained, oh, well, we've got this scheme where we can get exponential suppression on one axis for a linear price on the other. My background is architecture. And it's like, you go with that. Okay, and so this has proved to be a wise move up and down the line. But bottom line, you can see that some of the earlier experimental data here, it behaves as predicted. So what we end up getting, okay, you can't see it because it says because of the site here. So a typical superconducting qubit, ballpark, 100 microseconds to error statistically, either phase or bit flip. Similar technology. Cat qubit, we can get up to 10 seconds. Actually, we've gotten, considerably better than that in extreme cases. I'll be talking shortly here. But then our phase error, frequency is going up to a microsecond. So it's a couple of orders of magnitudes worse, but about 6 orders of magnitude better on the other axis. Okay, so it's an interesting thing. So that's exciting. But of course, there are problems with it. So I just described how the thing auto stabilizes on the bit flip axis. Doing a Hadamard is actually kind of going against nature in this universe. And so we don't do direct physical Hadamards as a general rule. There are some other things that are kind of tricky for us to do, but because the objective here is to build an error-corrected machine, then what's happening at the physical qubit level is less important than what it allows us to do at the logical level. So we can synthesize a Hadamard, a logical Hadamard, using some collection of these qubits, even if we don't have a native Hadamard function. So there's sort of some mappings that we have to do here. So we have to, the Toffoli that we would use, the logical Toffoli won't literally be the same as the one that we could have physically, et cetera. So that's a problem we've got to solve. The team has been working on this. There are multiple solutions to this problem. One of them we've published, but as we're learning the technology and discovering what we can do, this is it's evolving. Another challenge, again, relating to the fact that the way the stability works. How am I going to do a CNOT? Okay, because again, a CNOT implies that I am going to do an inversion, which is somewhat going against nature if I try to do it in a naive way. And so, challenge, but some really good folks in the lab, and they came up with a scheme where you can sort of visualize this as the state is conditionally rotating around, but never actually crossing that 0 point in the center where we would lose our coherence. And so the way this is actually implemented from one of the papers isn't animated, but you can sort of see this is a low level, physical level here, how the control signals are being modulated to be able to create this effect. So it's crude, but it works. And as first experiment is pretty impressive. Time to do this operation is about 400 nans. So it's not too terribly bad. Again, this is all physical stuff. We're interested in building an actual error-corrected machine. So the arc of development here is kind of interesting because if I go back to, I guess, the first proper presentation of this technique was in 2020. This is when the Alsenbob cat qubit was using a transmon for readout. We didn't actually have any technique for doing readout any other way. And I don't think we're the only people that ran into some issues early on saying, oh, well, the cat is great, but I need to have a transmon associated with it to be able to control it and measure it. It worked, but up to about a millisecond, and then we hit a wall. And we did not initially understand why we hit that wall at a millisecond. And it turns out it was the presence of the transmon and its effects on the rest of the circuit that was doing this. So going to last year, we published this improved design, which eliminates the transmon entirely. We can basically do the readout from the buffer itself. It's a simpler circuit, and it has upped the quality to by a couple of orders of magnitude there to where we're up to about 10 seconds. Okay, now for me, I'm an ex-Google guy. 10 seconds of stability on bit flip out of a superconducting qubit is remarkable. Okay, but we didn't stop there. There are some tricks that we can play. This is an experiment. I'm mentioning it because it's interesting, not because this is the direct path we're going down. This is still at a science phase. We're still doing research here. We're still discovering opportunities. We may open more paths than we have time to go down. And this may be one of them. Other people are working on behavior you can get out of squeezing, as they say, a cat qubit. We can sort of deforming that probabilistic circle a bit. And what that's doing, it's increasing the distance from the 0 point and thus increasing the stability. And so building the device, and it's an odd looking device. It's a large, complicated device with this kind of weird fractal looking resonator on the thing. I mean, if anybody did this in production, I doubt that they would do this, but nevertheless, we managed to get 160x bit flip reduction for, yes, sir.
What's the advantage of squeezing the cat qubits?
Essentially, it deforms the probabilities in a way that we reduce the bit flip, or put it a different way, we can get the same level of bit flip protection with a smaller number of photons in the oscillator, and therefore a lower error rate on the phase. So this is just one of these, again, it's the challenge that we've got. We can make the cat qubits extremely stable on the bit flip axis. The price we pay is on phase. So this is it's an optimization that we managed to pull off. Yes, sir?
Yeah, speaking of squeezing, are you sensitive to the phase of squeezing because of squeezing?
I do not know. I do not know. I have not heard that mentioned. But again, this was an experiment that was done. This was an experimental device that was done last year, results published earlier this year. There was, it was just somebody had this idea, wait a minute, this ought to work. Does it work? My God, it does. And so there is a paper. One of the things, you can always drop me an email. I can send you a point of the paper. I mean, one of the things I simply didn't have to do was just have a page with the QR codes of all the archives of all these things, just so that people could go directly to it. I don't know. But anyway, I mean, so, basically with this device configured, and again, this is not our primary best quality device. This is an experimental device for squeezing cats. Without the squeeze, we're looking at about 138 milliseconds of bit flip time, which isn't bad, but we managed to drive it up to 22 seconds by activating the squeezing. Yes, sir.
Can I just think about what's happening here is you've got these two coherent state blobs. They have overlap that is exponential in the separation. And as you move them apart, obviously that gets smaller, but you become increasingly sensitive to phase noise.
Yeah.
So you keep them a certain distance apart, but by squeezing them, you effectively reduce their overlap because now along that axis along which there are bit flips, the Gaussians sort of decay faster.
Yeah.
And then you have not moved them apart, so you've not increased their sensitivity to phase noise. Okay, so in that context, then yes, the like axis along which you do the squeezing is very important because it needs to be like sort of perpendicular to.
Oh, yeah, no, yeah, again, if that was your question, if that was, and I did not,
That's what I meant.
again,
The phase of squeezing, that's really the.
no, yes, exactly. It has to be controlled and on that axis. Absolutely.
Thank you.
Thank you very much for your kind support, gentlemen. And so I want to be clear, that device is not the device that was used for this experiment. Okay. But this is a recent experiment where we managed to get, I think basically an hour is in the confidence interval that we've got here. Some of the measurements went on for like significantly over an hour. Okay, but and again, I don't have to, and this is something where unfortunately the actual paper is still in the process of production. I can't provide a link to it here. The guys were so excited that they published a blog post on it there that has some detail. It doesn't have as much as I would like, okay, and it doesn't have as much as you would like, I'm sure. But nevertheless, being able to get an hour's worth of stability isn't bad. And one of the things that the researchers pointed out to me, which is in the slide, is that comparing the work here to some of the work that was being done at Google. One of the things that the Google people found is they were looking at repetition codes in particular and how things were stabilizing, is they were hitting a threshold that they felt was limited, was limited by something. They didn't know what. The best hypothesis was that it was external energy from some cosmic ray or other external event at high energy going through the lab. And we certainly, when I was at Google, we certainly worried about that, worked on shielding against that, that sort of a thing. The interesting thing is the Alice and Bob experiment didn't run into that. And we don't know why. So either the problems that Google documented were more subtle, or the mechanisms that we're using at Alice and Bob are a bit more resistant to that kind of an environment. It's not like we went to special efforts to shield things. So as I say, this is, really nice that we've been able to get this kind of stabilization and making remarkable progress over a relatively short period of time about getting stability times on the bit flip axis long enough to do meaningful computations. And we don't know what the limit's going to be yet. At some point, there's going to be a limit given a certain technology. But again, as I say, the price is we do have to deal with a higher degree of phase errors. But this is where something really interesting happens. This is what I think is really cool. And this has nothing to do with physics. This just has to do with engineering. Because what we did by breaking up the error correction problem into two components. So we are using physics to solve the bit flip part of the problem, which is, great and cool and elegant. But we've also reduced the dimensionality of the error correction problem from being a 2D problem to a 1D problem. And this has knock-on effects at a bunch of levels. So what we can do, and what most of the research has been just using a repetition code. And as it turns out, the code distances that we need don't actually seem to be too terribly bad. And so, again, we've got a the trade-offs here work in both ways. With the autonomous, as this slide refers to, the QEC of the cat qubit suppressing the bit flips, suppresses action exponentially at a linear cost. You can also look at how the repetition code is working, is that we are suppressing the phase flips exponentially with resources as the bit flips increase linearly. So it's this sort of this exponential linear trade-off happening at a couple of levels. And so this is sort of showing, again, the degree, the amount of overhead that we require to get to a fidelity that we're interested in is surprisingly low, quite manageable. And then furthermore, we can take this. I wish I had a proper slide to show this, but if I go back a couple slides here, because I guess there is I think there is a little image from Google here. So again, when Google's doing their repetition codes on their Willow and their other chips, I mean, it's a rectangular mesh that they're using, and they're just basically mapping a snake onto the thing. Okay, so you can visualize that we'd be doing the same thing on a chip with repetition codes, except that given that it's 2D, I can actually go to an LDPC. I can create some long distance connections and stay planar on a device. So where the people at Google and IBM and elsewhere are looking at, okay, yeah, we'll use LDPC codes for both axes. They're going from what was already sort of a 2D, 2.5D problem. This thing's really a 3D problem. There's a lot of work going into how do we construct devices to solve this problem? How do we build packages around this? That problem goes away for us because we've reduced the dimensionality of the problem. So we can do LDPC, 1D LDPC, 1.5D, I guess, if you like, keep that planar. And we can build a device that is essentially flip chip based concept, where we've got a couple different flavors of cat qubits interacting with one another, and we don't have this routing problem. It's a relatively straightforward thing to build. And this advantage in dimensionality, it just keeps coming up again and again. I don't know if you folks heard about this stuff, but there's some work that was published earlier this year. It's been sometimes referred to as the heart code. And so this is it's a magic state production scheme that ends up actually being a little bit better than the really nice scheme that Google proposed a few months earlier. And we were able to, again, collapse a problem that people had been conceptualizing in 3D by having lowered the dimensionality of the problem. We've turned it into a 2D problem, basically adding just a few ancilla to be able to planarize this. And so what we looks like we're going to get to is, first of all, fewer cycles for generating the magic states and fewer qubits required to do it. So this leads us to look like an architecture that is surprisingly simple to try to get to roughly 100 logical qubits in the next 3-4 years. And it's something we can fit into a single cryostat. And this is not the limit of what we can put in a device. So to me, what's really exciting here is, yes, we have to solve the problems of quantum communication between coherence realms, call them what you will. There was some interesting work presented here yesterday, great work going on here at Berkeley in this area. Getting things across distances, that's really important. Getting things around inside a machine room is going to be very important. But we have a unique advantage of being able to take advantage of only needing to communicate within a relatively small spatial volume to be able to do really large scale computations. One of the examples we've got here, and this is a moving target, changes all the time. But there was the famous excellent piece of work that Craig Gidney and others did at Google a number of years ago, saying how many qubits, raw physical transpond qubits, would I require to break RSA with a 2K key, basically factoring an integer that size using Shor's algorithm. And the initial estimate was 20 million in some number of hours, and it could work. And that was enough to really shake up the entire security industry right there. I mean, that's a revolution in and of itself. Never mind that that's a really big machine to have to build. So Alice and Bob, of course, have been using this as something of a benchmark. It's not a legitimate scientific benchmark, but it's sort of a resource high level, a roofline, benchmark, if you will. And so when they thought they would require 20 million, our estimate was we need about 100,000. Okay, and it's a heck of a lot easier to build a 100,000 qubit machine than a 20 million qubit machine. But my friends at Google are really smart. And so they've kept banging on this, and they've come up with some new schemes that really reduce that. So they knocked it down over the past year or two by a factor of 20, which is pretty impressive. And some of the problems that they solved are problems that Alice and Bob doesn't have. And so it's interesting here. So again, they changed the arithmetic they were using. They Gidney changed some codes, and they added their magic state cultivation scheme. So that takes them down to 1 million. Now, the thing is, some of these, the first of these is equally applicable however you're implementing the problem. Okay, so that's just everybody wins because somebody was smart. I love it when that happens. The second is that no, we can't actually use the yoked codes because we're not in that kind of a realm, but we can do the sort of 1.5D LDPC codes, which is metaphorically the same thing. So it's in the same spirit. And again, the magic state cultivation is extremely clever. What we're able to do with the hard code is also very clever, similar, comparable, we get an advantage. So no one has actually built the program yet, so I have to use an approximate sign here on 30K, but within a small, relatively small data, we're looking at what we can do, 30K qubits to break RSA. Or solve a really meaningful real world problem other than that, versus 1 million. And I can promise you, it will be a heck of a lot easier for us to build a 30K qubit system. It may be multiple cryostats, but it'll fit in a room. Versus 1 million, I mean, it's a challenge. I think 1 million qubit machines can be built and will be built, but we happen not to need to. So the roadmap we've got, we're developing devices. Boson was the first thing that demonstrated the cat qubit really worked. People could log on to Google, get access to the thing, and verify that it was stable for 10 seconds or so. Helium is the current chip that we've got in the lab. I'll just have one brief mention of that later because we're going to make that available to people. That was not the plan. The idea for Alice and Bob was go through these generations of chip, upping the ante, mastering a different technology at each step to get to, by 29 or so, the graphing machine, which would have these 100 logical qubits. And the plan had not been to sell these other chips. These are steps along the way. Boson is a single qubit. Okay, it won't run a gate. Okay, and what you won't run an entangling gate, and what you can actually run on the thing is incredibly limited, but it proves the point, and that was the whole issue. So similar, helium is not going to be a fully programmable universal gate set device, but it's an important device, and it was the device that we used to get that hour-long coherence. But we are going to make helium available. And some of you may be working in institutions where you've got a lab where you get in people's quantum chips and play around with them. I would strongly encourage you to talk to my colleagues here present if that's of interest to you, because it's one of these things where when we went into this, the plan was not to sell intermediate level chips, but very few people seem to know how to build these things. And so the more people play with them, the more we'll understand them. So I would encourage that, just think about that. So anyway, that was my, the sort of this overflight of what we're doing. But I guess that, the message here is there's a bit of cat qubits are an approach that works and seems to work extremely well. And that intuition of collapsing the dimensionality of the error correction problem is bearing fruit at multiple levels of chip design, packaging design, system design. I mean, it's just one of these things. Every once in a while, you hit on a scheme that just feels right. This happens to be one of them, at least for me.